Okay, working a couple of more examples of numerical integration. And this first one you might want to try by hand, just a little practice for the next test. And so we say use 4 intervals, and we're evaluating this function t cubed plus 4t, integrating that from 0 to 4. And so what you want to do is set up a table where you've put in your x values, which are going to be, of course, 0, 1, 2, 3, 4. For each one of those, we'll illustrate here on the graph, for each one of those you want to calculate the value of the function. So those values are shown here. And there's going to be connected by straight lines. And so the areas be calculated by the trapezoid area formula. So you're taking the average height. In this first one, it'll be the average of 0 and 5, multiplying it by the width here, which is just 1 unit, so that'll be 2.5. For the next one, the average is going to be 10.5, again multiplied by 1, and continue on for the other two. Sum them all up, and in this case you get an answer that the area under the curve, the integral there, is 100. Now go ahead and try to do that with Excel and use 8 intervals here. I'm not going to do that one. We'll do another one in just a moment. But you could set that up. Again, you want to use you want to go every half. So there's 9 points, 8 intervals, 9 values of y, but of course there are 8 intervals because you start with the second one. Average these two numbers, multiply by the difference here, copy that formula down, sum it up, and you get an answer of 97. Now the exact answer turns out to be 96, so you can see we're closing in on the solution as we use a few more intervals. Okay, here's the one I want to do. We're going to integrate e to the 3x times the sine of x with the limits of 0 to pi over 2 using 8 intervals. So let's set a column for x, and we're starting at 0. And again, we're going to an upper limit of pi over 2, and we want to have 8 intervals. So each one of those is going to be pi over 8. Pi over 16 rather. So I want to take the previous value and add to it pi over 16. And now if I copy that formula down until I get to pi over 2, you can see here I've got a total of 9 numbers. So there's 8 increments, or 8 intervals. Okay, now our y values, we just type in the equation. So equals exp for exponent of 3 times x, and that gets multiplied by the sine of x. Alright, we'll copy that formula down to the bottom, and now we'll calculate the areas. So starting at the second line here, I'll average these two values, and I'll multiply it by the difference in our two x values. And I'll copy that formula down. And at the bottom, let's sum that up. And so there is our answer, 34.561, let's call it. We can get that down to say 3 decimal places and center that up. So there's our answer. Now in just a moment, well, let's go back to the slideshow for just a moment here. And so there's our answer. Now it turns out if you do the exact one here, it's a little bit more of a complicated formula, which is one reason you might want to do it numerically instead of having to look the formula up. You see we're pretty close, 33.495 as opposed to our value of 34.561. So about 3% difference. And obviously if we used a few more increments, we'd be even better. So now what I want to do is let's look at the same integral, But now let's change the upper limit from pi over 2 to pi. And so what I have to do here, I can leave all this the same. I just have to change these values, these x values. Instead of adding pi over 16 every time, I'm going to add pi over 8. And so now we go from 0 to pi, and you can see our number is about 1,090. Okay, now if I do the exact solution for this one, it turns out to be 1,239. So we end up about 12% different here, whereas we were only about 3% different when we looked at a different upper limit. And so if we look at the graph, here's what we were looking at when we integrated from 0 to pi over 2. And so when we did our 8 increments, you can see that they follow really nicely. And so the areas under the curve, not going to be too much different. You can see we're overestimating a little bit at the upper regions. Now let's look at the same thing. If I graph that function from 0 to pi, a whole different shape. And when I look at what happens with the 8 increments, you can see, especially when I get to the upper region, that I don't estimate that, I don't follow that curve very well at all. So I ended up with a pretty large error. In this case, we underestimated by about 12%. So one way to make sure that you're getting a good answer with your numerical approximations is to use more and more increments until you find yourself converging to the solution. So again, in this case, that last example we looked at, the exact answer was slightly under 1,240, 1,239 point something. And so you can see even when we're using 10 up to 20 intervals, we're still got a pretty good error. But if we run subsequent analyses where I use more and more increments, when I get out here to 80, 100, even to 1,000, you'll see that the value is not changing much when we use more and more intervals. And so in that case, with MATLAB, it's easy to keep changing the number of increments until we see that we are converging. So just kind of wrapping up our numerical integration. It's really easy to estimate a definite integral using the trapezoid method. It's very easy to set up in Excel or in MATLAB, and you'll find it useful in a lot of different cases. In some cases, you don't know what the analytic solution is. Other cases, it might be pretty complex. And you're checking your hand calculation, checking your analytics solution, and making sure that you're close with your numerical integration does provide a good check. And sometimes too that instead of having a formula, you might have measured data points, and so you can integrate that instead of trying to fit a curve to it. You can integrate between those points. So again, you'll find that it's useful in a lot of classes going forward.